Today we're going to talk about acceleration. So if you Google the fastest car, you actually get two different types of results. So the fastest production car out there is the Hennessy Venom GT, and it can go about 435 kilometers per hour. The Ariel Atom here, it can't go that fast. But what it can do is it can reach 100 kilometers per hour in only 2.3 seconds. It can get up to speed more quickly. That is, it has more acceleration. So this Ariel Atom can reach a speed of 100 kilometers per hour in only 2.3 seconds. So we might ask the question, how much speed was it gaining every second? Well, it gained 100 kilometers per hour of speed in 2.3 seconds. So if we divide that out, we get a result of approximately 43.5 kilometers per hour of speed gained every second. And this is what we would call acceleration. At least in simple cases, and we'll talk more about what makes a simple case later, it's the amount of speed gained each second, or each unit of time. Now, more generally, beyond this simplest case, the definition of acceleration is the rate of change of velocity. And of course, a velocity is a vector, so acceleration, likewise, is going to be a vector. So as an equation, we can write that acceleration as a vector will equal the change in the velocity, which we might write as delta v, but of course a change in any quantity is really the final value of that quantity minus the initial value of that quantity. And in this case, these two quantities are vectors. And whenever we say that something is a rate, that means we're finding out how much of something changes per unit time. In other words, we're dividing by time. And I'm going to write that as a delta t to represent the amount of time it took to change from that initial velocity vector to this final velocity vector. And the units for acceleration, it's always going to be speed units per unit time. So for instance, we've seen kilometers per hour as the speed units, divided by seconds. How fast is the speed changing per unit time? You might see meters per second every second, which by the way can be written as meters per second squared, or the IB will write that as meters times seconds to the minus 2. So take care to note that it's always speed units per time unit. Now there are a few little things to watch out for when you're using this equation for acceleration. So let me walk you through that right now. You'll notice in this first problem that no directions are given. We don't know if this 10 kilometers per hour is to the left, to the right, north, south, up, down. We don't know that. But we can assume that these two speeds that are given are in the same direction. And we're going to assume that whatever that direction is the positive direction. So our final velocity would be plus 20 kilometers per hour, and our initial velocity would be plus 10 kilometers per hour. And that change in speed takes place over 5 seconds. So that's your time interval. So we plug in and we get an answer there of 2 kilometers per hour of speed gained every second. So acceleration is really a vector. If I want to put in the direction, I would say in the same direction as original motion. So now let's look at this second problem here. Once again, no directions are given, so we'll assume that this initial direction is in the positive direction, and this would be in the same direction as well. So our acceleration would be given by the final speed, the plus 10 kilometers per hour, minus the plus 20 kilometers per hour And once again, that's all done in a time of 5 seconds. So this time we're going to get a negative 10 minus 20 is negative 10 kilometers per hour in 5 seconds. So we get an acceleration of negative 2 kilometers per hour every second. And so our direction for the acceleration would be opposite to original motion. And we want to notice here that if direction is not given, negative acceleration implies slowing down, deceleration. Now things are a little bit different when we include the directions. Let's take a look at this example. So this time, because it's moving to the left, this would be a negative 10 kilometers per hour. This is also moving to the left because we know it was speeding up. So it would be going minus 20 kilometers per hour. And when we calculate the acceleration, we're going to get negative 20 minus negative 10. And that change would occur over a time of 5 seconds. So we're going to get negative 10 kilometers per hour of speed gained in 5 seconds, or an acceleration of negative 2 kilometers per hour every second. So the negative here implies an acceleration to the left. And notice in this case here, it doesn't mean it's slowing down. So negative acceleration doesn't really mean slowing down. It really means an acceleration to the left. So this car is speeding up, but it's speeding up to the left. So pause the video and try this question on your own and then come back for the answer. So your acceleration should be equal to the final velocity, and it's a positive 20 here because that's moving to the right. The initial velocity was negative because it was moving to the left. So we're going to have 20 minus negative 10 over a time period of 5 seconds. So our change in velocity here is going to be 30 kilometers per hour. And that occurs over 5 seconds. So we end up with an acceleration there of 6 kilometers per hour every second. So in other words, it started with a speed of 10 kilometers per hour to the left. Then we need to add 6 kilometers of speed to the right every second. So negative 10 plus 6 gives negative 4. So we would be going to the left at 4 kilometers per hour 1 second later. Another second later, it will have reversed directions and now be going at 2 kilometers per hour to the right, and then 8 kilometers per hour to the right, and continuing 14 and 20 kilometers per hour. Keep speeding up to the right. So it takes 1, 2, 3, 4, 5 seconds to reach a speed of 20 kilometers per hour to the right. So there's a big change in velocity there. Not a big change in speed, but a big change in velocity because of the reversal of directions. Let me briefly preview the idea of a turning acceleration, because the accelerations we've talked about up to now have been speeding up or slowing down. But another way for things to accelerate is just by their change in direction. So let's say we've got an object that does a path like this, so it changes direction. And we'll draw a velocity vector here at the beginning. We'll call that the initial velocity vector. Now a short time later, we could have it going the same speed, so I'll draw the length of the vector the same, but obviously it's changed its direction. So when we calculate the acceleration, it's a vector, and it's going to equal that v final vector minus that v initial vector, all over the amount of time it took to make that change in direction. And we discussed earlier how we subtract vectors. We can join them tail to tail, like so. Here's vi, here's vf, And the subtraction of the vectors goes from that initial velocity vector to that final velocity vector. This would be the vector delta v. This here, that would be the vector delta v. And then we'd divide that vector by delta t, and we'd get the vector for the acceleration. So as it turns out, the acceleration vector will always point towards the center of the circle. This would be the acceleration vector. And it would keep changing its direction, but it's always pointing towards the center of the circle. And the force that's making it turn would always point in the same direction. Experimentally, there's different ways to measure acceleration. One of the ways is with a ticker tape timer. And essentially what a ticker tape timer is a screw that goes up and down 60 times per second. And it hits a piece of carbon paper which leaves a mark on a paper ribbon. So let's suppose we attach our paper ribbon here to a cart, and that cart pulls the ribbon through the ticker tape timer. Then we're going to get a bunch of dots on that ticker tape timer. If the dots are equally spaced, then that would mean that we're going at constant speed. That's uniform motion. Because it was always the same amount of distance, and we know the time between dots is always the same. It's always 1/60th of a second. So it always went the same distance in the same amount of time. Whereas this object here, it's going bigger and bigger distances for the same amount of time. So it's speeding up. And this object here is, of course, slowing down. It's going smaller and smaller distances in 1/60th of a second. So it's slowing down. So let's see how we would calculate acceleration from a ticker tape timer. So we needed an initial velocity and a final velocity. So what I'm going to do is move my ruler up here and measure the distance between the first and second dot. Looks like it's around 0.7 centimeters. And I'm going to do the same thing for the last dots here. And it seems to be about 3.8 centimeters here. So I've measured this distance, found it to be 3.8, measured this distance, found it to be 0.7. So my initial speed is going to be the distance traveled, 0.7 centimeters, divided by the time taken. And the time taken would be the time between dots. Since it's 60 dots per second, it's 1/60th of a second for the time. And I do the same thing for the final speed. It's going to be 3.8 centimeters divided by 1/60. So effectively, I'm just multiplying by 60 in both cases. 0.7 times 60 gives me a speed there of 42 centimeters per second and a speed of 168 centimeters per second for v final. So if I want to calculate the acceleration, I've got v final, I've got v initial, and I've got to divide by the time interval. Now for the time interval, I'm really getting my v initial halfway in between these two dots. It was going a little faster than that here, and it was going slower than 42 centimeters per second here. So this is really an average speed, and we can take it at the time halfway in between the two dots. And the same thing here. v final really represents the instantaneous speed halfway between those two dots. And then let's see how many time intervals occurred. There'd be 1 time interval, 2 time intervals, 3 time intervals, 4 time intervals. Each time interval is 1/60th of a second. So my delta t is going to be 4 times 1/60, or 0.0667 seconds, which means my acceleration is going to be 168 minus 42 divided by 0.0667. Carry that out and you should get 1890 centimeters per second of speed gained every second. Strobe photographs are very, very similar to ticker tape timers in the way that they work. In a strobe photograph, multiple exposures are made at regular time intervals to produce a single photograph. And because you know the time between those exposures, you know the time that everything's occurring in the photograph. And of course, you can make measurements between the distance of objects at different times and calculate the acceleration, etc. We will also be doing video analysis, such as you're seeing in this picture here. I'm not going to explain that now, but it's actually very similar to strobe photographs and ticker tape timers. The most famous acceleration is the acceleration due to gravity, and you've probably heard of it. The acceleration due to gravity, usually written as g, is equal to 9.8 meters per second of speed gained every second. And often we'll round that and we'll say it gains about 10 meters per second of speed every second. So if I drop an object after 1 second, it would be going 10 meters per second. Then it gets going faster, so it's going to drop a greater distance here. And after t equals 2 seconds, it would be going 20 meters per second. And then it would drop farther still after 3 seconds, a bigger gap in space here. And now it would be going 30 meters per second. So it's gaining about 10 meters per second of speed every second. And that's for any object that's dropped, regardless of mass, but it's only true in the absence of air resistance. Let's finish off with a few questions. So we got a ball rolling down a curved ramp. At which position, the bottom or the top, is the speed greatest and is the acceleration greatest? Pause the video, try the question, come back for the answer. Well, the speed is greatest at the bottom, at B. Because the whole way down a ramp, of course, an object keeps gaining speed. However, at A, speed is gained the quickest. So in fact, it's dropping straight down at the beginning. So its acceleration would be about 9.8 meters per second every second. Or let's just round that. It's going to be about 10 meters per second of speed gained every second. But as we get down here, the ramp itself is helping to support the ball. Whereas right here, the ball could just fall down freely. So in that case, the acceleration is not going to be as great. It's going to be gaining maybe, say, 5 meters per second of speed every second. And when it gets flat, the acceleration is going to go all the way down to 0. So where is the acceleration the greatest? At the top, or at position A. We haven't looked at velocity time graphs, but maybe you can work this one out anyways. Pause the video, try the question, come back with the answer. So here's a VT graph, and here's the initial speed, and here's the final speed. And you'll notice the speed is gaining at a constant rate. Well, that means you've got uniform acceleration, constant acceleration. It's only true because we've got a straight line here, a constant rate of speed gain. And that means a constant acceleration, and here's the graph with constant acceleration. Pause the video, read the question, try it out, come back for the answer. So on the way up, of course, its velocity is up, and on the way down, its velocity is downwards. On the way up, it's slowing down. That means that its acceleration has to be opposite to its velocity. On the way down, it's gaining speed, and that means its acceleration has to be in the same direction as its velocity. So the answer is first in opposite directions, then in the same direction. Pause the video, read the question, try it out, come back for the answer. So if it's got a constant acceleration, it's going to reach a speed of 70 kilometers per hour at the halfway point in time. So if, for instance, it took, 2 seconds to reach a speed of 140 kilometers per hour, it would have taken 1 second to reach this speed of 70 kilometers per hour. But keep in mind, at the beginning, it's going slower. At the end, it's going faster. So if you're going slower, you don't go as far in the same amount of time. So the car is going to be in here somewhere at the halfway point in time. So the answer is A before marker 1. Let's summarize the big ideas from the video. So we said that acceleration is the rate of change of velocity. And we said we could write that as an equation. Acceleration equals v final minus v initial all over delta t. And we saw when we were using that equation that a negative acceleration implies slowing down if no direction is given. So if we're just told an object's moving at 20 kilometers per hour and we're not told it's right or left or north or south, then this statement will always be true. But in general, a negative acceleration would be a acceleration to the left or an acceleration that's downwards. And then we looked at ticker tape timers. We said that we could get an initial speed by looking at the distance between dots divided by, well, 1/60th of a second, the time interval between dots. And we could do that for a final set of dots as well. So we'd have a d all over 1/60 again. Then we could plug that into our equation, and our acceleration would be equal to vf minus vi all over delta t, where delta t is going to be the number of time intervals between the two sets of dots. So we'd have to essentially multiply the number of dots by 1/60th of a second to get this time interval. And that's all for today, folks. Thank you very much.